Good morning. So I am Aurélie Beynier. I'm from Leipzig in Sorbonne University. And my course will be about multi-agent resource allocation and matching. So today I will mainly focus on resource allocation, and tomorrow I will end with resource allocation and do matching. So first, I will give a brief introduction about the relevance of resource allocation problem in real life. Then I will define the problem, and we will discuss efficiency and fairness criteria and allocation mechanism. So this will be for today. So we will focus on the problem of allocating a set of goods. So we can call them resources, goods, items. The three terms will be used for the same thing. So we want to allocate a set of items among a set of agents. So for both setting, multi-agent resource allocation and matching, we will try to answer to three main questions. What kind of problem do we consider in multi-agent resource allocation and in matching? Which satisfaction criterion do we focus on? So what is our objective when we do resource allocation, for instance? And how can we perform the allocation of goods, of items among the agents? So this will be the algorithmic part of the course. So this course is mainly based on several books and surveys. So multi-agent resource allocation is a very active research area. And there are many surveys and very good books on the topic. So some of the papers that are cited on the slide have been written by people who are in the room or who will be in the room at the end of the week. And you can, if you want more details on some precise concepts that I will talk about, you can refer to the books on computational social choice. So the first one is the handbook of computational social choice. And you have a second part, which is related to more active topics today in the domain, which is trends in computational social choice. So both books are available for free on the websites of the authors. So we will first start with the problem definition of a multi-agent resource allocation problem. So in a multi-agent resource allocation problem, we have a finite set of agents. So the agents will be called A1 to AN. So here in the example, I have 3 agents. And we have a set of items or resources to allocate to these agents. So the set of items here is called R, and each item is R1 to Rm. And as you can see, we can have different size of sets. So most of the time, we will assume that we have the size of the set of resources is equal or larger to the set of agents, but this is not mandatory for all the settings. And so here you have the items are fruits we want to allocate to the agents. So you can see we have 4 fruits for 3 agents. And to allocate the items among the agents, we need to have preferences. So we will, agents will give individual preferences over the items. So for each agent, we will have her preferences among the set of items we have to allocate. So here, I suppose we have ordinal preferences. So each agent gives a ranking over the set of items. And we want to compute an allocation. So an allocation is a mapping which describe the resource we allocate to each agent. So here you can see the allocation A is a mapping of agent to bundles of resource. So we have the set of agents and all the possible bundles of resource, and we want to allocate a bundle of resource to an agent. Okay, so A will denote, capital A will denote the allocation, and AI will denote the bundle or the share of resources allocated to agent AI in the allocation. So we can find multi-agent resource allocation in a wide variety of real-life problems. For instance, you may want to allocate schools to students or universities to students, like in Parcoursup. You may want to allocate courses in a university. So you have different courses, for instance, for diploma in AI, and you want to allocate the different courses to the students based on their preferences. You may want to allocate rooms or dorm rooms to dorms to students. So this is for a scholar application, but you may also want to allocate public housing to families. You may also want to divide goods in inheritance or divorce, and you want to separate the goods between the members of the couples. And you may also want to manage resources on a cluster or in grid computing. You may want to allocate tasks to nodes, or you may want to allocate computing time. You may also want to schedule manufacturing tasks among different people or different area in to build object, or you may want to allocate tasks in a multi-robot system. Imagine you have robots that have to explore an unknown environment. So you will have different tasks to perform in the environment, and we want to allocate the task to the robots. So the resources and the items we want to allocate have different characteristics, and the algorithms and the methods we will use will change depending on the characteristics of the items. So first, you may want to allocate divisible or indivisible resources. So divisible resources can be divided into several different shares. Then you can distribute to the agent. So for instance, you can have a cake and you want to divide the cake between different agents. So you can cut the cake and give a different part of the cake to the agents. You may also want to allocate water or electric power to different agents. So this is some resources that you can divide. But you may also want to allocate indivisible resources. For instance, a book, an house, a seat in a course. So a student cannot share the same seat. if you divide a book, you won't be able to understand the book, and you cannot divide a job, for instance, if you want to allocate job to people. So the first part, the first type of resources is divisible resources, are mainly studied in a domain which is called cake cutting. And I will not focus on this part of the domain of multi-agent resource allocation. Resources can be shareable or non-shareable. So a resource is shareable if you can allocate it to several agents at the same time. So for instance, you can share buses, train, boat to several agents. And note, this is indivisible resources. You cannot cut the boat or the train, but it can be used by different agents at the same time. Resources can be static or not. So static resources do not change their properties over time. So they cannot be consumable resources or perishable resources for which the quantity of resources or the utility of the resources change over time. You can have single unit or multi-unit resources. So a single unit resource is a resource that can be distinguished from the other resource by its name or by its characteristics. For instance, you can have several boats, but each boat has a specific name. So one boat is shareable, but each boat is single unit, even if you have several boats to allocate to the agents. And you can have resources with positive value. So for instance, it may be a fruit, a house, boat, and so on. And you can have resources with a negative value. So positive valued resources are called goods, and negatively valued resources are called chores. So for instance, it can be tasks to allocate to the agent. And if you consider that the tasks are time consuming, the agent will like to have few tasks and to minimize the utility, the negative utility of the task, so of the chores they have to perform. So in this course, I will mainly focus on divisible, non-shareable, static, and single unit goods, so positively valued resource. So this is the main part of all the papers that are published in multi-agent resource allocation. So as I said before, we have agents, we have resources, and agents will give their preferences over the resources. So the preferences will express the satisfaction of an agent when he obtains the resource or when he obtains a bundle of resources. So a bundle of resources is a set of several resources. And we call a preference structure the preferences of an agent over the set of resources of the set of bundles that can be allocated. And we have different ways to represent the preferences. We can use ordinal preferences. So in ordinal preferences, each agent will model his preferences with a binary relation. So here we index the binary relation of the resources or the bundle of resources by the name of the agent, the ID of the agent. And we will say that a bundle L1 is preferred by agent I, is preferred to bundle L2 if agent AI weakly prefers the bundle L1 to the bundle L2. So we have weak preferences, but the preferences may also be strict. So in this case, we have this notation for strict preferences. So it means that the agent strictly prefers bundle L1 to bundle L2. We can also use numbers to represent the preferences. And in this case, we have cardinal preferences. So each agent will have a utility function, which will map each possible set of resources, so each possible bundle of resources to a real value. There are other types of preferences, but I won't detail them in the course. So to compute the allocation, we need the agent to give their preferences. So we need a representation of the preferences. So we can use explicit representation. For instance, in a utility function, it means that we have to enumerate all the bundles, all the possible bundles of resources. And for each possible bundle of resources, we have to give a utility. So this is for one agent, and we have to do this for each agent. If we use ordinal preferences, we can also enumerate all binary relation between two bundles of resources. And of course, the number of alternatives to enumerate is exponential. And it is often not realistic to ask the agent for this representation of their preferences. So we often seek for a succinct representation language, which will exploit the regularities of the domain to give more compact representation of the preferences. So to have a good representation language, we will want the language to be succinct, so to have a compact representation of the preferences. So to measure the succinctness of a language, we can use the average or worst size of the representation. And we can compare different representation using this succinctness criterion. So this is the first thing we are looking for when we define a representation language. We also want the representation language to be expressive, so to allow to represent all the preference structure of the agent. So some representation language will not be able to represent, for instance, synergies between resources. And if you don't have synergies between resources in the preferences of the agents, that will be okay. But you have to be aware of the possible preference structures the agent can give you to define the good representation language that is able to represent all preference structure. Once you have the preferences of the agent, you will use them to compute an allocation. So you will have to be able to compute the utility, for instance, of a bundle based on the compact representation of the preferences of the agent. So imagine you have a utility function which is additive and gives the value of each resource. When you have a large set of resources, you must add all the utility of the resources which belongs to the bundle. So this is quite easy. but you may have other representation language where the computational complexity of the computing the value of a bundle is higher than just summing over the resources of the program. And as you want the agent to give you their preferences, you will have to elicitate the preferences of the agent. So we will have to ask the agent for their preferences. And we want the language to be easy for the agents to describe their preferences. So if you imagine that your agents are humans, you will ask the preferences for instance, when you want to divide goods in an inheritance, you will have to ask for each of the people involved in the inheritance for each of the kids, for instance, to give them their preferences, and it must be easy for the agents to give their preferences. And if you have the description of the preferences, it must also be, you also want them to be understandable. So given a preference representation, it should be easy to understand the structure of the preferences of the agents. So this is for the properties that we want the preference language to fulfill, but we will see that for the different representation language, it's not always, we don't have always all the properties together. So in this course, we will focus on additive valuation functions. So in the cardinal case, you can assume that the agents gives you the utility for each single item of the set of items to allocate. And when you want to compute the value of an allocation to an agent, you sum over the items allocated to the agent, you sum the utility for each item. So this is a quite common valuation preference representation that is used in many papers, and it is quite simple to describe, simple to understand. It is very compact because you only have to enumerate the value of the single items and not the combination, not all possible value of all possible subset and bundle of resources. But the main drawback of this representation is that it cannot represent synergies between resources. For instance, if you have an apple and you have for instance a banana, so you have you give the value for the apple alone, you give the value for the banana, but maybe you like fruit salad when you have both banana and apple, and having both fruits is much better for you than having the fruits, the sum of the fruits alone. So the super additivity of the fruits is not represented in additive valuation. So one extension of additive valuation is k-additive valuation function, where you allow for synergies between set of resources of size at most k. So in this case, when you have a bundle of resource AI, you will consider all the possible subsets of resources you can make with the resource in AI, and you will sum the value of the synergy value of these resources. So you will have the value for the apple alone, the value for the banana alone, and you will have a synergy value that you will add for the apple and banana together. And this synergy value is 0 if the size of the subset is larger than k. So that means that we do not allow for synergy between set of items larger than k. So we don't have to care about a larger set of resources. This allows to limit the computational overhead when you want to compute the value of an allocation. So there are other representations which comes from logics, for instance, weighted propositional formula, and you also have a succinct representation in the ordinal case, and I give the references if you want to have more details about this representation. In the rest of the talk, I will assume that we have additive valuation, except in, I think, one specific case, but you can assume that we have additive valuation. So if we come back to our initial problem, so in our MARA multi-agent resource allocation problem, we have a set of agents, a set of items. So as I said before, we consider non-shareable, positively valued, don't remember all the assumptions. Indivisible, there is a mistake here. It's indivisible, non-shareable static resources and single units. And we assume that we have a compact representation of the preferences of the agents over the items. And we want to compute an allocation which maps to each agent a set of resources. Since we don't consider non-shareable resources, that means that if we take two allocations, the allocation of two agents, the intersection will be empty. So we don't have items which are allocated to different agents. An item is allocated to only one agent. And we will say that an agent prefers an allocation A to an allocation A prime if the bundle allocated to the agent prefers to in the allocation here, the prime should be here. We prefer A to A prime if the bundle allocated to the agent AI is preferred by the agent to the bundle he would obtain in A prime. And if we have a cardinal representation, in fact, we will compare the utility. So we will compare the utility for the bundle allocated to the agent in A prime to the utility allocated of the bundle allocated to the agent in AI. And in the rest of the course, we will try to answer to the question, to the following question: what is a good allocation? So here we can compare two allocations from the point of view of an agent, but we have a set of agents. So how we decide what is a good allocation for the whole set of agents, and how do we measure the quality of an allocation? Once we have a criterion for measuring the quality of an allocation. We will try to compute an allocation, and we will answer to the second question: how can we compute an allocation with a good quality given a specific criterion? So now, to evaluate the quality of an allocation, we will talk about efficiency and fairness. So in fact, in multi-agent resource allocation problem domain, we can have 2 points of view to measure the quality of an allocation. We can focus on the efficiency of an allocation. For instance, we want to maximize the global utility. So we will sum the utility of all the agents, and we will try to maximize the sum of the utilities. In this case, we don't want to waste resources. We want a complete allocation, because wasted resources won't give utility. So we will try to maximize the global utility function without wasting resources. So it follows the utilitarian theory, which comes from economics, and it's okay if you have agents who won't compare their bundles and who won't complain about their allocation. For instance, if you have multi-robot systems and you want to allocate resources to the robots won't complain about the allocation. The objective of the designer of the system is to maximize the efficiency of the multi-robot system. So you can use a utilitarian theory. The objective is to maximize the efficiency of the whole system. But in fact, if you have real humans as the agents, and the humans are in fact a little bit selfish, they will compare their bundle of resources, and you are likely that they will complain about the bundles they obtain if you want to maximize the global utility of the system. So the second point of view is to take the fairness goal and to try to compute an egalitarian solution for the agents. So in fact, fairness and egalitarian theories are very old principles, because you can find in Aristotle works references to egalitarian theory and to what we call equals of equals, where he says that human often complains about an allocation if they have the feeling that they are equal, but they have not been treated as equal. So it's what we call equals agents should be treated as equal. And if the agents don't have the feeling to be treated as equal, you are likely to have complaints about the allocation. So when you want the allocation to be adopted by the agents of the system, it's always better to use a fairness perspective than an utilitarian perspective. But if you have agents which are only concerned by maximizing the utility of the system, you can use efficiency perspective and utilitarian theories. So now, how we define the efficiency or the fairness of an allocation? in fact, there are different ways to measure the efficiency or to define the efficiency, and we will see that there are different fairness criterion to measure the fairness of an allocation. So if we consider the efficiency, the first efficiency criterion is completeness. We want all the resources to be allocated. In the case where resources are positively valued, it's obvious because when you allocate a resource, you obtain a positive utility. Where if you don't allocate the resource, you will have 0 for this resource. So if you want to maximize the sum of the utility, you should allocate all the resources. So this means that if you take the union of all the bundles of resources allocated to the agent, you obtain the set of resources to allocate. So this is the first requirement. The second is Pareto efficiency. So an allocation is Pareto efficient or Pareto optimal if there is no other allocation where all the agents obtain at least the same utility, and for at least one agent, the agent obtain a better utility. So that means that you have no other allocation where you can improve the utility of at least one agent without decreasing the utility of all the other agents. So of course, if you can improve the utility of one agent and all the utility of the other agents remains the same, you will prefer this allocation to the other one. So this is natural requirement. So here I formalize the definition. So an allocation A is said to be Pareto optimal or Pareto efficient if and only if no agent can improve our utility without decreasing the utility of another. So you can have many Pareto efficient allocation, Pareto optimal allocation. And then you have to choose between these different Pareto optimal allocation. And one way to select the most efficient allocation is to use the utilitarian social welfare. So this is the sum of the individual utilities of the agent. So you sum over the set of agents, the individual utility of all the agents. So you want to maximize the global utility of the system. It means that all the agents will agree on the fact that the most important thing to do is to maximize the welfare of the system. Okay. So this is for efficiency. So we have also you can focus on fairness, and you have different way to measure the fairness of an allocation. And if you look at the literature, there is no common agreement on the measure that is really relevant in all cases for measuring fairness. So the first thing, there is a problem with the slides. All this should be on the same line. So the first way to define fairness is equitability. And an allocation is said to be equitable if all the agents will enjoy the same utility. So it means that there exists an allocation where you can give the same utility to all the agents. And of course, you will try to maximize this utility. Because if you give nothing to all the agents, every agent will have a utility of 0. So you are equitable, but you are not efficient. So you want to be fair, but as efficient as you can. When you have indivisible resources, finding an equitable solution may not be possible because you may have to split a resource to have exactly the same utility for all the agents. Imagine you have two resources, so R1 and R2, with two agents, N1, A1 and A2, and you have first agent have 10 and 2, second agent have, for instance, 4 and 8. So in this case, if you want to give the same utility to both agents, you can give a utility of 6 for the agents, but you you can give a utility of 9 to both agents, but in this case, if you give R1 to A1, it has 10, and R2 to A2, you have 8. So you have to transfer a part of R1 to the agent A2 to have exactly the same utility. And without dividing a resource, you can't have the same utility for all the agents. So in the domain of indivisible resources, equitability is rarely studied. A second criterion is egalitarian social welfare. So in the previous slide, we had utilitarian social welfare when we want to maximize the sum of the individual utilities. In the egalitarian social welfare, you want to maximize the minimum utility of the agent. So you are looking, you take the minimum over the set of the agents of the utility of an agent. So in fact, you look at the utility of the worst of agent in the system, and you will want to maximize the egalitarian social welfare, so to maximize the utility of the worst of agent. You may have a different allocation that give the same egalitarian social welfare. And you may also have large differences between utilities among the agents, because you only consider the worst of agents and you do not look at the utility of all the other agents. So you may have a different allocation where, for instance, you may have an allocation with 3 agents, A1, A2, A3, where you have 3, 5, 5, 4, and 9, no, 6, 4, 4. So in this case, the utilities of the agents are quite the same. And in this case, you have 2 agents with the minimum utilities and 1 agent which have a higher utility. So the difference is not very large in this case, but you may have allocation with larger differences in the utilities. And in the egalitarian social welfare, you ignore the utilities of all the other agents. Another criterion is the proportional fair share. So in fact, in this case, you measure the utility of each agent for the whole set of resources. So here, this utility is the utility of the agent I when you give to her all the resources. And as you have n agents in the systems, you divide this utility by n. So it is called the proportional fair share of the agent. And the idea is to give to each agent a share that is value at least as his proportional fair share. So you want each agent I to have an allocation which is for which the utility is greater or equal to his proportional fair share. So in fact, you can you assume that from the point of view of the agent, it will consider that the whole set of resources is divided equally with an equal value among all the agents of the system, and you want the agent to have at least the value he would obtain if he will divide the value of the whole set of resources by n. And an allocation is said to be proportional if all the agents obtain their proportional fair share. So note that the proportional fair share of an agent is computed based on his individual utility function. So the agents of the system may have different value for their proportional fair share. And proportional fair share allocation is not guaranteed to exist. So in this case, if we reverse here the value and we change them a little bit. So in this case, the proportional fair share of the first agent is 10 plus 2 divided by 2, as we have 2 agents, so 6. And the proportional fair share of the second agent is 8 plus 3 divided by 2, so 5.5. And as you can see, both agents prefers the first resource. So we will have to give it to one of the agents. If we give the, R1 to agent A1 and R2 to agent A2, the first agent will obtain his proportional fair share as it obtains a value of 10, which is strictly greater than 6. But the second agent will obtain a value of 3, which is less than his proportional fair share. And if you reverse the allocation, you have the same problem. Then A2 obtains his proportional fair share, but A1 does not obtain proportional fair share. So there is no, in this instance, there is no proportional allocation. There's an allocation that is proportional for each agent. Okay. So another fairness criterion is max mean fair share. So the max mean fair share of an agent is the maximum value the agent could guarantee to herself by partitioning the items. So the agent make the bundle and choose for her the worst bundle. So in fact, it consists of a mechanism called I cut, I choose last, or in the 2-agent case, I cut, you choose. So imagine you have a cake. In this case, this is a divisible resources. You have a cake, you cut the cake, and you will be the last one to take the part. So when you cut, you imagine that you will get the worst part of the cake. And in this case, you can try to cut the cake to have the best, worst part of the cake. So this is what we call max mean fair share. So here you maximize over all possible allocation. Pi is the allocations. So you maximize over all the allocation the worst utility you can obtain. So the minimum of the utility you can obtain in this allocation. So in fact, this is the best utility the agent can hope if all the agents have the same utility. So the agent AI, when he cuts the cake, he assumes that all the agents have the same preferences as her, and he will obtain the worst part of the cake. But in fact, in the allocation problem, all the agents can have different preferences, and when the agent who cuts anticipate the worst part, if the agents have different preferences, maybe he will obtain a better part than the worst part, because the worst part for her is the best part for another agent, and the other agent will take it and he will have a better part than the worst part he anticipates. So the existence of a max-min fair allocation, so this is an allocation where each agent obtains a utility that is at least is max-min fair share. So the existence of such an allocation is not guaranteed, but in fact, building a counterexample is not so easy, because you have to consider problems where there is many resources compared to the number of agents in the system. So in fact, there is a result with an intuition which says that for any set of players, so of agents n, such that the number of agents is more or equal to 3, there exists a set of items of size m, and this size is of the set of items is at most 3n plus 4. So if you consider that you have 3 agents, you may have to consider a set of resources 3 by 3 plus 4, so 13. So you may have to build an example with 13 resources and 3 agents to find an instance that does not admit MMS allocation. So if you search for an counterexample where there is not MMS allocation, and you consider problems with a small set of resources compared to the number of agents. So for instance, you consider 3 agents and 5 resources, or 3 agents and 4 resources, and you search for an MMS allocation in this case, you are very likely to not to find an counterexample, so an instance where there is no MMS allocation. So you can do experiments and generate random instances and check for the existence of an MMS allocation. And if you consider small set of agents and small set of resources compared to the number of agents, you won't find a counterexample. You have to consider larger set of resources to find a counterexample. But there are some counterexamples exist. The existence of MMS allocation is not guaranteed. So 2 more fairness criteria, and it will be finished with a fairness measure. Another way to measure the fairness of an allocation is to make the product of the individual utilities. Because if you look for the egalitarian social welfare, as we consider here, as I said before, you don't consider the different value of all the other agents And you may have very large differences between the value of the agent. So one way to consider the differences between the utility of the agents is to simply make the product of the utilities and to search for the allocation which maximizes the Nash product, so the product of the individual utilities. So it will favor high individual utility value and equal utilities distribution among the agents. So for instance, if you consider an agent with an allocation when you have 10, 2, 3, and an allocation with 5, 5, 5. So the Nash product of the first one will be 2060. And the Nash product of the second one will be 125. So you will prefer this allocation where, in fact, you have quite the same utility for all the agents. And if you consider the sum of the utilities, you can see that the sum of the individual utilities is the same. But in this case, utilities are more equal between all the agents. They are equal in this case. But you will favor this kind of allocation. And the last but not least fairness criterion is envy-freeness, and it's one of the most studied fairness criterion, which in fact consists in each agent comparing its utility to the utilities he will obtain if he gets the bundles of the other agents. So it's quite natural when you obtain a set of resources, you will compare it with the set of resources obtained by the other agents. And an allocation is said to be envy-free if no agent prefers the bundles of another agent over a own bundle. So we compare the utility for the agent I, we compare the utility he obtains with her bundle to the utility she will obtain if she gets the bundle of another agent. So it's quite natural and easy to explain and to motivate. But the main drawback of envy-freeness is that when you consider the case of indivisible resources and you want to allocate all the resources, an envy-free allocation may not exist and often does not exist. If you consider the case with two agents, you have two agents and you have one candy to allocate to the agent, one resource. Both agents like the resource and you have to give the resource because you want the allocation to be complete. And obviously, the agent who don't obtain the resource will be envious of the other agent. So you cannot compute, you cannot find an envy-free allocation if you are in the indivisible case and and you want completeness of the allocation in this case. Okay, but there exist instances in the indivisible case and under the completeness assumption requirements where you can find an envy-free allocation. If you take the previous example here, so you have 3 here and 8 here. If you allocate R1 to agent 1 and R2 to agent 2, you have an envy-free allocation. Because if you give to the agent 1 the bundle of the agent 2, he will obtain utility of 2. And in this case, with her bundle, she obtains the utility of 10. So she's not envious. And the agent 2 obtains a utility of 8. And if you give her the bundle of the other agents, she will obtain a utility of 3, so she's not envious, and you have an envy-free allocation. Okay. So envy-freeness is a Boolean notion. So you are envy-free, you have an envy-free allocation, or you don't have an envy-free allocation. And when you don't have an envy-free allocation, you may want to maximize to minimize the degree of envy. And in this case, you have to measure the envy of the agents. So there are different ways to aggregate the envy of the agents. So first, you can measure the envy between pairs of agents, so between I and G. So this is the maximum between the utility. So this is the utility of I towards G. So you measure the NV, and you take the max between the difference of utilities and 0. So if the agent is not envious, the NV will be 0. Otherwise, the NV will be given by this difference and will be positive. So this is the NV between for I towards G, and you can compute the NV of the agent I by taking the maximum NV she can experience towards the other agents. So you consider all the other agents, you measure the NV for each of these other agents, and you take the maximum. So if you envy agent 2 by 3 and agent 3 by 4, your NV will be the max, so it will be 4. But you can also take the sum of the bilateral NV. So in this case, you sum over the other agents, the NV experience for these agents. So this is for the agent, the individual NV, and then you can aggregate for the whole set of agents. And to aggregate for the whole set of agents and to have one measure of NV for the whole allocation, you can take the max over the agents, or you can make the sum over the agents. And in this case, you want to maximize the global NV. So you may want to maximize the max over the agents of their NV, which is the max over all the other agents of the bilateral NV, or you can combine max with sum or sum with sum and so on. So you have a different way to define the measure of the global NV of the system. Okay, so we have different measure of fairness, and in fact, we can find some relationships between a subset of these notions, and it has been proved by Bouvray and his collaborators that under additive preferences, in fact, if you have envy-freeness, if an allocation is envy-free, it is also proportional, and it is also max-min fair share. So in fact, you have an implication between the different notions of fairness, which is in this side, and it is proved that is not there is no equivalence, so you cannot go from the right to the left. So I think I have examples. So here, some examples to fix the different notion and implications. So we have 3 agents and 4 resources. And in the first case, you can see, so we have here cardinal utilities. So the first agent values the first resource to 10, the second to 6, the third to 1, and the fourth to 6. And you have different preferences for the second agent and for the third agent. And in the first case, we can find an allocation that is envy-free. This is the blue one. So you give R1 to A1, R2 to A2, and R3 and R4 to A3. So we can see first that the allocation is max-min we can see that it's proportional. So the easiest is to compute the proportional fair share of each agent, as the sum of the utilities of the agents is the same for all the agents. We have, in fact, the same proportional fair share for each agent. The utilities of the items sum to 21 for all the agents. So for all the agents, we have the proportional fair share, which is the utility for the whole set of agents, 21, divided by the number of agents by 3. So the proportional fair share of each agent is 7. And you can see in the blue allocation that each agent obtains strictly more than 7. So each agent obtains a proportional fair share. So the allocation is proportional. 23, maybe. Yes, 23, but it's okay with 23. Okay. So we can prove that the allocation is envy-free. So if we consider the first agent, so it obtains 10. If he gets the bundle of the second agent, he will obtain 6. So it's not envious of the second agent. If he obtains the bundle of the third agent, he will obtain 1 plus 6. So 7, it is not envious. For the second one, if she obtains the bundle of the first agent, she will obtain 6, which is less than 10, so not envious. And here he obtains 7, so he's not envious of the third agent. And we can do the same for the third agent, which is not envious of the first one and of the second one. And for the max-min allocation, so if we consider, for instance, the first agent, so the first agent will consider that all the other agents have the same preferences as her preferences. She divides the set of resources, and she will take the worst possible bundle, and she wants to maximize the value of the worst one. So the worst will be 6, because you have to make 3 bundles. So you can make 1 bundle with the most value resource. Then you have the last third one. And in this case, you have to make 2 bundles with R2, R3, and R4. So you have to maximize the value of the worst. You have to make 1 bundle with 6 and 1 bundle with 6 plus 1. Otherwise, you will have 1 bundle with 6 plus 6 and 1 bundle with 1, and your worst utility won't be maximized. So the max-min share of one of the first agents is 6. So there is also a mistake here. So this is 6, and the agent A1 obtains more than 6. So he obtains his max-min share. The same can be applied to agent A2 and A3. So the max-min share of these agents is 6, and the agents obtain more than 6. So they obtain their the allocation is max-min. In the second case, So I have changed the preferences of the second and third agents. And in this case, you can see that there is no entry-free allocation. In fact, the first and the second agents have exactly the same preferences. And if you can see that the agents who obtains the highest utility among A1 and A2 will be envious of the other one. So in this case, if we give R1 to agent 1 and R2 and R3 to agent 2, agent 1 is envious of agent 2, but if you give R1 to A1 and another bundle among these three resources, then A2 will be envious of A1. So there is inevitable envy between these two agents. So there is no entry-free allocation, but you can find proportional allocation. Like in the previous case, the proportional fair share is 23 divided by 3. So in this case, all the agents obtains their proportional fair share. And the allocation is also max-min allocation for the same arguments as in the first allocation. So you can see in this case, if we come back to the implication, in the first case, we have entry-freeness, proportionality, and max-min share. In the second case, we don't have entry-freeness, we have proportionality, and we have max-min share. And in the last instance, we don't have an entry-free allocation. In this case, all the agents have the same utilities for all the resources. So we don't have entry-free allocation. We don't have a proportional allocation because in this case, one of the agents will have a bundle of 6, or you can give the R2 and R3 to the same agent, and you are with the third one will have a utility of 1. So the utility is 6 or 1 for at least one agent, and this agent don't have his proportional fair share. But in this case, the allocation is max-min because the max-min share is 6, and all the agents have their max-min fair share. And as I said before, you have to consider a larger set of resources if you want to find an allocation where there is no max-min allocation. If you want to find an instance where there is no max-min allocation. So in the third case, you don't have entry-freeness, you don't have proportionality, but you do have a max-min share. Okay, so so we have seen that an entry-free allocation may not exist. And if we consider entry-freeness, in fact, we can define, we can use a relaxation of entry-freeness. So different relaxations have been proposed recently in the literature. The first one is entry-freeness up to 1 good. You consider that you are envious of another agent, but if you remove one of the items of the share of the other agent, you won't be envious of these agents anymore. So in fact, an allocation is envy-free up to 1 item if the envy of the agents, so in this case, the envy of A1 towards AG, can be eliminated by removing one of the items of the agents who is envied. So we consider for every couple of agents, there exists a resource which belongs to the second agent, such that if we remove this resource from the set of resources of the other agents, the utility is less than the current utility of the agent. So the agent is no more envious of the other agent. So this is a notion that is weaker than, less demanding than envy-freeness. And in the weak additive case, so you can say in the additive case, envy-free up to one good allocation is guaranteed to exist. So we obtain the guarantee of existence, and it can be computed in polynomial time. So we will see it in the next part of the presentation, but in fact, it's easy to compute an envy-free up to one good allocation. More demanding notion that is between envy-free up to one good and envy-freeness is envy-freeness up to any good. So in this case, you are envious of another agent, and you are envy-free up to any good if you the envy can be removed by removing any of the other items of the other agent. So in fact, in envy-free up to one good, you can remove one item and remove the envy. In the second case, you become non-envious whatever the item you remove from the bundle of the other agent. So in this case, in fact, you will remove the items you value the most to remove your envy. If you can remove your envy when you remove the item you value the most from the other agent, you will be you can be envy-free up to one good. But in this case, it must be true for any items of the other agents. And in fact, for the item, you value the least in the bundle of the other agents. So if you take the value, the item for which the value is minimal for you in the bundle of the other agent, and you remove this item, if you become non-envious of the other agent, then you are envy-free up to any good. So this notion is much more demanding than envy-free up to one good. And clearly, if you are envy-free, you are envy-free up to any good, and you are envy-free up to one good. And if you are envy-free up to good, you are envy-free up to one good. And in the general case, in fact, the existence of an envy-free up to any good allocation is an open problem for the community. And many researchers have worked on it, have done experiments by generating randomly multi-agent allocation resource instance and try to find an envy-free up to any good counterexample. So an allocation where we don't have an EFX allocation. And at the moment, we don't have counterexample. So nobody found an instance where there is no EFX allocation. For some specific case with a small set of agents or specific valuation function, it has been proved that an EFX allocation always exists. So the guarantee of existence is proven for specific case, but in the general case, it is not shown. And it is one of the challenging research issue in multi-agent resource allocation today. As a side note, because I mentioned previously the Nash welfare. In fact, in this case, the Nash welfare may be interesting because it has been proved that an allocation which maximizes the Nash welfare is always envy-free up to 1 good and Pareto optimal. So if you want to find an EF1 and Pareto optimal allocation, you can directly use a program which maximizes the Nash welfare. How many times? Okay. So you have envy-free relaxation, and you also have proportionality relaxation as and proportional allocation may not exist. Like in this case, we don't have proportional allocation. So you may want to relax the notion of proportionality. And it's quite the same as in the envy-freeness setting. So an allocation is as proportional up to 1 good if you can find 1 item, and if you add this item to the bundle of resources you obtain, then you become proportional. So you have the utility here, you have the current utility of the agent in the allocation. You add to this allocation a resource which belongs to another agent. And then by adding this resource, the utility becomes greater or equal to the proportional fair share. So the agents become, the allocation of the agent become proportional. A proportional up to 1 good allocation is always guaranteed to exist. And it can also be computed quite easily by a round-robin protocol. So I will explain it later. And you also have proportionality up to any good. So in this case, here you have, there exists 1 resource R such that if you add R, you become proportional. In this case, for all the resources R which are located to the other agents, if you add the resource to your bundle, you become proportional. So it must be true for all the resources, all the items allocated to the other agents. So in particular, for the resources, the agents value the least. So if you take the worst resource allocated to the other agents and you add it to the bundle of the agent, then the agent becomes proportional. And in this case, you have proportionality up to any good if it's true for all the agents. So like in the envy-freeness setting, if you have proportionality up to any good. And if you have proportionality up to any good, you have proportionality up to 1 good. And then you can add this to the implication you have seen before. So we said that envy-freeness implies envy-freeness up to any good, which implies envy-freeness up to 1 good. Proportionality implies proportionality up to any good, which implies proportionality up to 1 good. And you also have an implication between envy-freeness up to 1 good. So envy-freeness up to 1 good implies proportionality up to 1 good. So this link is described in this papers. Okay. So we will finish today with some complexity results. So here we don't consider the complexity of computing the value of a bundle. So for instance, we assume that we have a representation of the utility function which enumerates the value of each possible bundle. So we don't worry about the complexity of computing the value of a bundle. if we consider the efficiency notions, so deciding if an allocation is Pareto optimal, is co-NP complete, and finding an allocation with maximal utility, utilitarian social welfare is NP hard. If all the valuations are additive, so the case described before, it is polynomial. For fairness notion, so finding an allocation with maximal egalitarian social welfare, so we maximize the utility of the worst of agents, it is NP hard, even if all evaluations functions are additive. So we don't have the easiest case as we have for efficiency. And computing MMS allocation, or even computing the max mean share of an agent, so the max mean share for only one of the agents of the system, it is NP hard. And deciding whether NP-free allocation is NP complete, whether an NP-free allocation is possible, it is NP complete, and whether an allocation that is both NP-free and efficient, so we want NP-freeness and Pareto optimality. So in this case, it is sigma 2p complete. So to sum up the complexity results, you can see that we have difficult problem to solve. And tomorrow I will detail how we can compute allocation which which are guaranteed to satisfy one of the criterion or several criterion if possible. Okay, so tomorrow we'll turn to the allocation mechanism of the multi-agent resource allocation problem.